A yield criterion problem using von Mises stress is now going to be applied to a shaft. So we see in our picture here we've got a shaft with a given diameter. Applied to it are two external loads. We have an axial load P and a torque T. And we're asked to determine the magnitude of the torque T for which yielding will occur when P has a value of 240 kilonewtons. So to do any of the yield criterion problems, we need principal stresses, sigma 1, 2, and 3. So we're going to need to do a stress transformation. We're going to end up looking at a critical piece on the shaft. We'll look at a piece on the outside of the shaft, so something on the exterior. And let's look at the state of stress at that point. The internal forces are directly the same as the applied external loads in this case. So we're going to have in the x direction, which is along the longitudinal axis of the shaft, we have a P over A. And then looking at the shear stress caused by the applied torque, we would have a value of TR over J. So to get this started, I'm going to do this all symbolically here. In the end, we'll end up plugging in numbers. Again, the only unknown that we have is the applied torque T. So we'll take a look at the initial states of stress. On the X face, we've got P over A in tension. On the Y face, 0 shear stress. Again, it's forgiving in this regard, but on the X face, we would have a shear stress that would cause rotation for Moore's circle in the clockwise direction. Somebody is positive. And negative TR over J for shear stress on the Y face. Take those 2 points directly to Moore's circle. So we're going to plot the X point. I'll put it right there. Put an X by it. I'm going to call that P over A, TR over J. Y point, put right down here. Put a Y by it, 0 comma minus TR over J. Connect those 2 points. By doing that, we have now found the center of the circle. And that's just going to be at P over A plus 0, quantity divided by 2. So that's just going to be at P over 2A. We need the radius R of this circle. So we need this length. And that length is going to be TR over J. In this direction, we go from P over 2A to P over A. So that has a length of P over 2A. So we can fill in Pythagorean theorem. Also looking at the spin of Moore's circle, we would see sigma 1 sitting on the other end, sigma 2. And going back and looking at the problem, we're on the outside edge, so we're on a free surface. So sigma z is equal to 0. So the z point would be sitting right there. So with that, we know that sigma 1 is going to be the center plus r. Sigma 2 is going to be equal to 0. That's the next principal stress. And then sigma 3 would be the center minus r. I'm going to use C minus r in our derivation. We'll work through the criterion, von Mises. And so you see the formula there. It's the difference in all the principal stresses. When that is equal to 2 sigma yield squared, then we have yielding. And so when they're equal, that would be just before yield. So this equation we are going to manipulate, and then we're going to end up meeting with our r squared equation. So to start with, we're just going to plug in what we know for sigma 1, 2, and 3. So sigma 1 becomes C plus R minus 0 squared, plus sigma 2, which is going to be 0 minus C minus r. You have to be very careful with your signage in here. Sigma 3 minus sigma 1 is going to be c minus r minus the quantity c plus r. And that would equal 2 sigma big Y squared, sigma yield squared. And going back, I forgot to square that entire quantity. So at this point, we're just going to continue to simplify and manipulate and multiply this thing out. So I'm going to take my time here, c plus r squared plus minus c plus r squared plus, and a c minus a c inside there, so we're going to end up with 2r, minus 2r quantity squared is equal to 2 sigma yield squared. Multiplying this out, that would be the first term. Second term, we'll end up with the c squared and r squared. In the middle, we'll have minus 2cr. And then the last term would be 4r squared equal to 2 sigma yield squared. Again, I like to say yield to make sure we're not confusing that with sigma y. Some simplification, we get cancellation there. 2c squared plus 6r squared is equal to 2 sigma yield squared, ending up with 6r squared is equal to 2 quantity sigma yield squared minus c squared. So we end up with r squared is equal to 1/3 sigma yield squared minus c squared. And so we're actually just about done. We've got r squared is equal to 1/3 sigma yield squared minus, and I'm just going to plug in the value for the center of the circle, which was p over 2a. And now we're just going to equate these two. So I'll draw a line. This one up here now can be equated to this expression right there. So r squared can be substituted in for each other, and we'll end up with one equation. So writing this, tr over j quantity squared plus p over 2a quantity squared would be equal to 1/3 sigma yield squared minus p over 2a quantity squared. So all we have is math left to finish this problem. We're going to end up solving this equation for t. As we look through it, the only thing unknown is T, the applied external torque. And so if you go ahead and do that, this would be your expression for T squared. Quantities we're going to have to use: polar moment of inertia, R for the radius area, sigma yield, and also the value of P. Plugging all that in, we end up with an expression for T squared. Take the square root, and we'd end up with the answer 828 Newton meters.